for 16, this is quite a common kind of problem in planning nowadays, right? And this is what I will do in lab as well. So if let's say you have this compound N and you boil with NaOH, basically this step is whatever they want to react it with, right? You know, sometimes when you do organic synthesis, right? Let's say you want to synthesize A, so you will use B and you will use C to form A. But how do you know your U is 100%, correct? There might still be some B left and there might still be some C left. So how are you going to separate them to get only A? This is one method, right? So in order to separate B, A and C, you have to, you can separate them based on their acidity and basicity, right? For example, if A is the acid, right? If B is a base, and if C is a base, what you can do is you can throw in acid. If you throw in acid, the two bases are going to be protonated, right? So it's going to be like BH plus and CH plus, and A will just remain as it is. And then now what you can do is you can put water inside, right? If you put water inside, you'll know that this will most likely dissolve in water, and this as well, right? While this, it will most likely enter the organic layer, right? In other words, it doesn't dissolve in water. So now if you put them in a separating funnel, right, you will see two distinctive layers. One is the aqueous layer, one is the organic layer, right? So this organic layer contains A, while this aqueous layer contains BH plus and your CH plus. Then you can go ahead to drain away the aqueous layer, and you will only be left with the organic layer, and therefore separating them, right? Of course, there are other ways to separate them, but this is the most basic way, right? And the concept is quite simple to understand. Or, right, instead of adding acid, you can add base, right? If you add base, your A, right, this one is adding acid. Now if you add a base, right, A will be deprotonated, it will become A minus, while the two bases, nothing will happen to them, C and B, right? So now what you can do is, again, you can just add water, right? But now A minus will go inside the aqueous layer, while B and C will remain in the organic layer, right? And then you can just drain away the aqueous layer, and then you will have A inside your aqueous layer, right? But we are not interested in getting the aqueous solution of A minus. We are interested in getting A, correct? So what can you do to obtain A? Remember just now you deprotonated it, correct? So since now there's only A minus in it and tons of water, you can just throw in an acid to protonate A minus, right? So once you protonate A minus, you'll go back to A. It's again insoluble in water, correct? So you will just partition out as another layer. So now you have the pure water layer and just A. And then again you separate them, remove the water, you will get back A. Okay, This is what I always do in lab as well, although it sometimes can be quite troublesome, but it's very, very helpful, right? So this question is basically related to this concept, right? And just for info, which layer is denser, the organic layer or the aqueous layer? Organic, right? A lot of students say it's organic, but the correct answer should be, it can be either or, depending on their density. We always say organic layer is less dense because we know that oil floats on water, right? But oil is just one kind of organic solvent. There are other organic solvents which are denser than water. For example, your CH2Cl2. This is a common organic solvent called dichloromethane. It is in fact denser than water, right? Its density is about 1.33, while water is 1, basically, right? So it depends, right? And of course, there have been questions which ask you to label the two layers as organic or aqueous. So please pay attention to the density, right? So let's go back to 16. For 16, first step, you boil it with NaOH, right? So if you boil it with NaOH, what will happen is that this Br will remain where it is, right? There's no SN2 because of conjugation with this pi bond. Right? I already mentioned this before. Afterwards, there's an amide bond. This amide bond will be broken. You'll form COO minus on this side and your NH2 on this side. Right? And then you have a Br here. So this Br is going to be replaced with OH as well. And don't forget to draw your Br minus. Right? So after reacting with NaOH, you have these three species, this, and this. Afterwards, you want to separate them because you want to obtain only maybe only one of them. What you do is you add organic solvent, right? Or you can add aqueous solvent, doesn't really matter. So if you add organic solvent, it's going to dissolve all the uncharged molecules, right? Which is very obviously the center one. While your aqueous layer will contain this and this, right? So this is aqueous, this is organic, right? And then you can proceed on to the questions, to the choices. The first choice, the compound in the organic layer has 4 stereoisomers. Yes, right? You have one chiral center here, and then you have another chiral center here. So 2 to the power of 2 is 4. 1 is correct. The compound in the organic layer turns hot acidified K2CCr2O7, your dichromate, from orange to green, which is correct because you have a secondary alcohol. It will be oxidized to ketone. And the last one, when aqueous layer is treated with acidified AgNO3, 1 mole of cream precipitate is obtained, which is correct because you have your Br minus, which will react with your Ag plus. Okay? So 1, 2, and 3 are all correct. 17. For the first part, predict a pKb value, right? So if you compare the N-methyl cyclohexylamine with cyclohexylamine, you know that N-methyl cyclohexylamine is secondary, while the first one is primary, right? So we have learned that secondary has a stronger inductive effect, which makes it a stronger base, right? So a stronger base means a smaller pKb. So you just have to write a pKb that is smaller than 3.3, but not 1, of course. Right? But not too low. You can write 2 or you can write 2.5, up to you, right? As long as it's lower. Right? Explanation already explained, right? There are 2 electron donating groups, so the lone pair is more available. This one should be fine. Next, 2 propylamine reacting with methanol twice, right? So if you react once, you can see that after this reaction, after you react once, this is what you will end up with, correct? So if you react with it another time, this is what you will get, basically. Just follow the same trend, right? So this is the final product. Relatively straightforward. And then the last one, when phenylamine undergoes this reaction, the yield is very low. If you can recall, I already said for phenylamine it is slightly less reactive, right? Although it's still very reactive. So for this case, the lower reactivity is due to the lone pair delocalizing into the ring, right? And they already told you that this is a nucleophilic addition reaction. So since the lone pair can delocalize, it is a weaker nucleophile, right? So you have to talk about 1 phenylamine is weaker nucleophile. So why is it a weaker nucleophile? Is because of the lone pair delocalized into blah blah blah. This part should be okay, right? This answer is quite standard. And then the third point is the delocalization causes the lone pair to be less available for nucleophilate addition, right? So it's just these 3 points. Right, let's try 20. have done the test, you realize that the part 1 and part 2 are basically similar to my question 1, correct? So it's actually just derived from the prelim question, right? So explain why the R group has a smaller pKb than the R group in lysine. Right, this reason I already explained before. So a smaller pKb means it's more basic, correct? So why is it more basic than the R group? Why is it more basic than the R group in lysine? What's your answer? A lot of students will say that there are 3 nitrogens, right? So therefore it's more basic, therefore it's a smaller pKb, which is wrong. Right, so what's the reason for the smaller pKb? Remember when we talk about basicity, we talk about availability of the lone pair, right? For this case, if you consider lysine, it's like that. If you look at arginine, it's actually like this. Right? So instead of talking about the availability of the lone pair, you can talk about the stability of the conjugate acid, right? By first protonating them. So if you protonate lysine, this is what you will get. If you protonate arginine, this is what you will get, right? So now the question is, which one is more stable? And the question really gives you the hint by giving you that equilibrium, right? So if you were to look at, compare these two, these will be more stable, right? The reason is because of, once again, resonance. So if you were to draw the resonance structure, you will see that for arginine, you can have resonance structures like this. This is the first resonance structure. Of course, this nitrogen also has a lone pair, so you can also participate in resonance. And this is what you get. Right? So you can have 3 resonance structures, or for this case, no, there's no resonance structure. So based on your ARIO rule, for both of these, the atom is the same. For resonance wise, only this can have resonance, but for this, there's no resonance. So obviously this will win out, right? And therefore, it's more stable, therefore more basic, right? So for your explanation, you have to talk about the conjugate acid of your arginine is more stable, right? Why is it more stable? It's because resonance can occur which disperse the positive charge right. So therefore arginine is more basic. So it's just these 3 points, right? And you can also tell from the resonance structure that the positive charge is delocalized over the 3 nitrogen atoms, which stabilizes it as well, right? Therefore, that's what is meant by resonance can occur which disperses a positive charge. Okay, this is for part 1. And then for part 2, suggest the reason why the R group in arginine will not undergo a second ionization in water. So this is once again your conjugation explanation, right? So out of these 3 nitrogen, only this is truly basic. Why? It's because this lone pair delocalize this lone pair is also delocalized, right? So delocalization means that it is less available, and I've explained in the video that this is exactly the same as your phenylamine concept, right? So for your phenylamine, why are phenylamines less basic? Is because this lone pair is delocalized over the ring, right? Why can it delocalize? Is precisely because of this system, which is identical to this part, right? And in fact, this delocalization is even better. Is because of this nitrogen, which is electronegative, right? You pull the lone pair away from this nitrogen, while for this case, the ring is just carbon, it's not electronegative. So for this case, it's more effective. Okay. So why the R group in arginine will not undergo a second ionization is because of the, once again, lone pair delocalized, right? Lone pair delocalized into pi bond. And then you can further talk about the electronegative nitrogen pulls the lone pair towards itself, right? And then making it less available. Since this question is basically talking about, is asking about why it is not basic, right? So you have to link back to the availability of the lone pair. So therefore, right, the second nitrogen has low basicity. Therefore, we will not undergo second ionization, right? So it's just these 3 points. Next, really show you the structures, and same thing, it gave you 3 pKb value, they give you 3 pKa values, so you have to assign it, right? Think of that as pKa, not pKb, right? So you have these 3 groups, and if you assign them, right, this nitrogen will have pKa of 12.48, this will be 9.04, and the last one will be 2.17, right? The reason I already explained in the test video. So make use of these pK values to suggest the structure of the 2 species present in aqueous solution of arginine at pH 3, right? So now at pH 3 it is more basic than this COH, so we'll have to deprotonate it. It is more acidic than this, so we have to protonate it, right? And it is more basic than this, so we have to protonate it as well. So this will be a species present at pH 3, right? But they want you to suggest the structure of 2 species present in an aqueous solution of arginine at pH 3. So we must definitely change one, correct? But how come there can be 2 species present in an aqueous solution at arginine? If you can recall from the last lesson, when I draw the pH line, right, I told you that there can never be a point whereby you have 100% of these species. It's always a mixture, otherwise it won't be called equilibrium, right? So we know that at 2.17, actually it can be explained by this line, right? So it should be somewhere here. You have 2.17, you have 9.04, and you have 12.48, right? So pH 3 lies somewhere here. So within this region, you should have 2 species, right? So what are the 2 species? We can go the long way so that we don't get wrong, right? At 2.17, everything is going to be protonated, so you're going to have the COH, H3N plus, and at the bottom here, you're going to have a NH2 plus, right? Which is this group. I just abbreviate it, right? NH2 plus. There's here, right? While at 12.48 everything is deprotonated, so we have CO minus H2N, and you have NH, right? So between here and here, the 12.48 is going to be protonated, so it's going to be H2N, COO minus, and your NH2 plus. And for this region, you're going to have this 9.04, which is this group, H3N plus, COO minus, and your NH2 plus, right? So if you count the net charge, here is plus 2, plus 1, 0, and minus 1, right? So now if you have pH 3, which is here, right, which group are you going to have? Which two groups are you going to have? You're going to have these two groups, isn't it? Right? How do you know it's these two but not these two? Because 3 lies closer to 2.17, right? Remember, at the midway between here and here, you're going to have the most amount of this, right? Afterwards, this is going to decrease, this is going to increase for this part. Understand? In other words, the graph is going to be something like that for these species. Let's see, 50. If this is 100. I draw using a color. Okay. So if I draw the proportion percent, if let's say this is 50%, midway 50, we know that at this point we are going to have 50% of this, 50% of this. Same thing for this point, right? So if we draw the line, we're going to have something like that. The proportion of this species, right? You have learned this in your ionic equilibrium. At pK, you're going to have 50-50, right? This for this species, red species. So for this species, I use blue. And never mind, this one easier, right? If it's this species, I use blue, right? It'll be like that, and so on, basically, right? So at pH 3, which is at this point, you're gonna have these two species. If I were to draw these two line, right, it'll be like that. Okay, so therefore your answer should be this plus this. Can So if you are confused, you can always go back to this method, right? Field proof. So now write an equation to show how arginine maintains the pH when a small amount of acid is added to an aqueous solution of arginine at pH 3, right? So since you already established that we have these two forms, right? These two forms differ by only a H. So this is the same as, if you want to represent it A minus, this is the same as a HA, right? So I believe you know how to draw write the equation, right? The buffer equation if you add acid. If you add acid, A minor is going to react with it to form HA. So you just have to draw these species plus the H plus to become these species, right? In the last question, right? Similar to all naturally occurring amino acids, the solubility of arginine is lowest at its isoelectronic point. Explain why that is so, right? I didn't go through this, so I'll go through now, right? The definition of isoelectronic point is the point whereby it is neutral, right? Now we know that if it's neutral, it must have the equal amount of positive and negative charges, correct? So what will happen at this point is that just nice is neutral, and just nice it can form a very, very well balanced ionic structure, right? You can just draw this indefinitely, right? And so on. So what if it's not at isoelectronic point? Let's say if it's at this point, right? If it's at this point, we know that there's a net plus 1 charge. So if we were to draw diagrams like this, right, we'll have positive charge here, negative charge here, maybe another positive charge somewhere else. But we know that the net charge of this is positive, right? So if this net charge is positive, do you think it is easier or harder to put another amino acid beside it? It'll be harder, correct? Because they will repel. Compared to this case, it's more favorable, right? So since for this case it will repel, do you think dissolving it is easier or harder? It will be easier because it doesn't like to be in the ionic form. Or for this case, it prefers to be in the ionic form, therefore it's harder to dissolve, right? In order to put this into words, you have to say that at, right, isoelectronic point, which is your PI, I just use it to represent it, net charge is 0, right? This means that your lattice energy is it greatest or smallest? Remember, ionic lattice is negative. You can either say highest magnitude or most negative, right? But don't use largest or smallest, it's big. So lattice energy is the most negative, right? If it's the most negative, that means, right, you will need a lot of energy to break apart ionic lattice to dissolve. So therefore solubility is lower, right? This is in terms of your thermodynamics. Energetics, right? Okay, so you can try the last one, question 29. first part, explain one advantage, right? This is not really a chemistry question, right? So they already told you that bromine, bromine is toxic, right? Did you say? Did not see? Oh yeah, they say avoid handling bromine directly, right? This means that bromine must be toxic. And we know that bromine is a liquid. And pyridinium tribromide is an ionic salt, which means it's solid. So handling solid is easier than handling liquids, right? So that's the answer for part 1. And then draw the structure of the tribromide ion Br3-. So we know that it's a linear, it's connected in this fashion, right? It's not linear, by the way. So we just have to draw in the electrons, right? So for this bromine, we know that if we draw a dot and cross versa, we know that it must be connected in this way, right? You're quite familiar with it. And then the central bromine, 1, 2, 3, 4, 5, 6, 7, correct? And then you have a negative charge, so you should go to the central bromine as well, right? This is the dot and cross, and then you just have to convert it to your line bond diagram, right? Which is like that. And then you have 1, 2, 3, 4, 5, 6 negative, right? Usually put the negative on the outside, right? You put inside also, never mind. So for this case, this shape is quite obvious that it's linear, right? I shouldn't have drawn it bent, right? It's linear because we have 3 lone pairs here surrounding it, which gives it a linear shape, right? This is your chem bonding. And then for part 3, what type of reactions are step 1 and 2 of route 1? For step 1 is a condensation reaction, right? You are removing small amounts of ethanoic acid, or you can say that it's a nucleophilic acyl substitution, whereby this ethanoate is being substituted away, right? So you have your NH2R attacking here, right? This is just for your info, right? O minus, and then you have NHH. Anyways, the mechanism already went through. Afterwards, you just come back down and kick away the ethanoate, and then you have the amide here. Step 2 is a electrophilic substitution reaction. This one is quite obvious, right? So route 1 is the preferred route because it produced mostly monobrominated anilide, while route 2 produced the multi-brominated. So if you can recall from our lesson, I already said that this is actually the trick in getting a mono-substituted phenylamine, right? You first deactivate it by making an amide, and then you hydrolyze it eventually, right? So the reason is the same as what I went through. It's because your amide, it's a weaker electron donating group, right? As explained here. So therefore, it activates the ring only weakly compared to the second one, which activates the ring so strongly, which results in multiple substitution. Question 5. 4-bromo anilide is formed from step 2 of route 1 at 88% U. And they ask why not the 2-bromo anilide. The reason is because of sterics, right? If you have gone through the test, you will know that it's the same concept actually, right? About sterics. So you'll prefer to substitute at the 4th position, which is furthest away from the amide group. And then the last one, describe and explain the relative basicity of the 3 nitrogen-containing compounds. So the most basic one will be the first compound, right? Phenylamine itself. And then the second one will be the central one, and then the least basic is your amide, right? Why is it a central one? It's because of bromine being an electron withdrawing group, which makes the lone pair less available. And for the amide, the lone pair is delocalized into a carbonyl group, which is even less available than the other two, right? One more thing to take note, right? If you have your phenylamine reacting with your con HNO3 and con H2SO4, right? What will the product be? What would the product be? Phenylamine reacting with con HNO3 and con H2SO4. There we go. This one? Is it? This one? Tri-substituted nitro product, is it? You only, yes, you only get a mono-brominated product, a lot of mono-nitrated product, right? A lot of students fail to see this, right? But it's a very, very easy question. You have phenylamine, you react with con HNO3, con H2SO4. The first step is going to be protonation. Because, like what I always emphasize, acid base is always the fastest. So once it becomes NH3, a lot of students didn't realize that NH2 is here, NH3 plus is here, right? So NH2 is an activating group, NH3 plus is a deactivating group. If it's a deactivating group, your NO2 will go to the third position, right? And you only have one NO2 because the ring is already deactivated. There's no way for you to get multiple substitution, right? So this is the answer. So don't get tricked, okay? Alright, let's look at electrochem. Right, that's more or less it for nitrogen. So, can you attempt the true false first? I already placed one page of the electrode potential values inside, right? On the second page. This is quite a long topic. This is one of my most hated topics, right? Because it can get confusing sometimes. Anyway, MnO2 is a solid. It's not liquid. 10 first. We go through a summary first, because the last few questions need more time to think, right? So let's look at some basic terms, right? So I believe you all know what is redox already, right? But take note of some new terms, right? Disproportionation is a redox reaction where the same species is simultaneously oxidized and reduced, while the opposite is called comproportionation, right? So don't get confused. The second one is not disproportionation, right? First one is 1 become 2, the second one is 2 become 1, right? Some oxidation state assignments. For all these rules of oxidation state, you actually don't have to know, right? Because all can be derived from the concept of electronegativity, if you think about it. For the first one, oxidation state of atom is 0, of course, because there's nothing for it to attract, right? Since it's only itself. Second one, oxidation state of atoms in homoatomic species. Since it's homoatomic, everything is the same atom. So even if you have a bond, the electron is shared equally, right? So it doesn't go closer to either one, so therefore oxidation state is 0. Third one, oxidation state of more electronegative atom is negative, which is of course because it gets greater share of that electrons. Fourth one, oxidation state of hydrogen is +1 except in metal hydrides. Why is it always +1? Is because when you connect it to any atom, it should be more or less more electronegative than hydrogen. So hydrogen really gets nothing, so therefore it has an oxidation state of +1. Except in metal hydrides is of course once again because compared to metal, hydrogen is more electronegative, so the 2 electrons is closer towards hydrogen. Is again electronegativity concept. Oxidation state of F is -1 in all compounds. This is because F is the most electronegative already, right? Oxidation state of oxygen is -2 because it's the second most electronegative, except in peroxides because hydrogen only have 1 electron, right? This is logical. And OF2 because, like what I said, F is the most electronegative. So if it's bonded to O, it will be F which is getting the electrons. So once again, it's quite logical to think about it. Next, sum of oxidation state of atoms equals to charge of species. This one is already, you know, from O levels. And the last one, change of oxidation state usually occur to the less electronegative atom because it's easier to remove electrons from them, right? So basically the above rules originate from the concept of electronegativity. Understand the trend in EN and use the plus-minus method, which I told you all 2 times before, right? One in chem bonding, one in one in organic chem. So now we can try to attempt example 1, right? They come from different topics. First one should be quite simple. BaO2. Barium is from group 2. If connected to O2, barium can only have oxidation state of +2 since it's from group 2, right? Which means this case your O2 is actually O2 2-, right? How do I get O2 2-? O2 2- is not O- and O- combined together, right? O, if you can recall the structure of your hydrogen peroxide, this is the structure of your hydrogen peroxide, right? H2O2. If you deprotonate it once, it will become like that. If you deprotonate another time, you become like that, right? So O2 2- is actually this species, right? Not O- times 2. Take note, right? You have learned transition elements already, so the second one you can try. Maybe you can try drawing the structure first, that will help you. non-periodic table because I thought it's not needed. So it's a square planar complex, right? Or tetrahedral, but doesn't really matter. So this is what you should be getting. If you can recall from your transition elements, there are different kinds of ligands, right? Some ligands, you all know what's ligands, right? Some ligands are negatively charged, some ligands are neutral, right? So for this case, it's basically testing you on whether you know how to classify the ligands. For this H, right, it's actually H minus. This is your Cl minus, this is your H minus, right? What about this group? What about this ligand? This ligand is actually a neutral ligand, right? Because this is what it is, right? When we move on to transition elements, I'll teach you how to identify whether it's negatively charged or neutral, right? So for now, you just have to know that this is a neutral ligand, these three are charged. So since the overall charge of this complex is 0, that means rhodium must adopt a +3, right? Then next, for this organic molecule, once again, I've already told you this method, the plus minus method, right? So if you compare carbon and hydrogen, carbon is more electronegative, right? Hydrogen is 2.2 in electronegativity, carbon is 2.5. So if you use the plus minus method, right, you have carbon bonded to these two hydrogen, and for the oxygen wise, oxygen is more electronegative. Since it has a double bond, that means you will draw the double positive and minus, and then you just count the net charge around this carbon, which is 0, right? So this is 0, and then next I can go ahead to count this carbon first. For this carbon, right, you have like that, and you have 3 minus plus minus plus minus plus hydrogens. So around this carbon, the net charge is -2. 0 minus 2. Now what about this oxygen? If you think that counting electrons around this oxygen is too hard, you can apply rule number 7. Right? Sum of oxygen state of atoms equals to charge of species. You know that hydrogen is +1 and you have the 2 carbon. You can come up with the charge, the oxygen state of oxygen easily, right? So I will not go through that because you can just apply 7, right? So we go through the next part. Balancing redox equations. This one shouldn't have problem, right? You already learned this in chapter 1. But this is method 1, which is the slow method, right? And this is for the case whereby the half equation is not in data booklet. So after you learn electrochem, you know that data booklet actually contains a lot of stuff, and you can just apply method 2 directly, right? But don't just learn method 2, they can give you something which is not inside, right? So same thing, first step, copy down the reduction half equation, and then you invert the reduction half equation responsible for the oxidation, right? Because you have 2 halves of the equation. Multiply by appropriate integers, and then you add the 2 half equations. For basic solutions, you just have to neutralize H plus by adding equal amount of OH minus, and then you cancel common terms. Okay, so you can try example 2. The first two are the first two organic molecules are prelim questions, right? should have the first one by now. Huh? So I just apply method 1, right? So I just follow step by step. Writing the equation is really written, right? Balance all elements except O and H. So I balance Cl first. Left hand side I have 1 Cl, right hand side I have 2. Just write a 2 here. I don't care any other elements, right? Just everything except O and H. Cl is balanced. Let's look at this. Sulfur. Sulfur is also balanced. So everything is balanced. Okay, next. Balance O by adding H2O on the other side, right? For this I have 2. On this side I have 1, 2, 3, 4 oxygen. This side I have 1, 2, 3, 4 oxygen. So oxygen is balanced. Next. Step 4. Balance H by adding H plus on the other side. So for this side I have 2H. For this side I have 0. So I have to add 2H plus on this side. Right? Afterwards, balance charges with electrons. For this side, is it balanced? The electron is balanced, right? The charge. So that's all. Right? Straightforward, right? And then for second one, although it's organic molecule, the idea is identical, right? I just apply method 1 again. Balance all elements except O and H. For this case, I know that the carbon backbone doesn't change, right? Apart from that, my N is still there, my oxygen is still there. So it's balanced everything. Next, I balance O by adding H2O on the other side. Is O balanced? O is balanced as well. Left, right hand side both got 1 O. Nitrogen, same thing, right? Next, balance H by adding H plus on the other side. So are the number of H's the same? If we just look at this portion, right, we know that the rest of the structure never change. Right? We have this becoming this. Right? So if we just apply some basic logic, we know that this hydrogen is gone. Right? This hydrogen is gone as well. So in order to balance these two hydrogens, we will have to add 2 hydrogen plus, right, 2H plus on the right hand side. And then I go ahead to do step 5, balance charges with E minus. So since this side there's 2H plus, I just balance it with 2E. It's exactly the same, just that it become organic, that's all. So can you try the third one and the fourth one? The fourth one, as bio students, you shouldn't have a problem, right? You should know what's the fourth one, right? It is what? Your NADH become your, sorry, your NAD plus become your NADH, correct? If you can recall the equation, good for you, right? If not, then you just have to apply method 1. So actually you don't even have to look at the structure, right? You know that it's NAD plus to NADH. So you just have to balance these, right? So H, you just add a H plus here. And then electrons, you just have to add 2 electrons here. Right, that's all. You can go check with your bio notes. I think it should be the same, right? So after we establish some basics, we can look at electrochem already, right? So the first concept is your electropotentials. So how these arise, right? So if let's say you place a metal, a piece of reactive metal in its ionic solution, two processes will occur. First is that the Mg will dissolve to become Mg2+, and the reverse can occur as well. So now when the rate of the two reactions or the two processes are equal, you establish an equilibrium, right? So at equilibrium, the rate of both equations is the same, and we can represent it with this equilibrium equation as well as an equilibrium constant. We just call it K. So far okay, right? So how do we actually measure this K? Right, it was found that this K is actually related to a term known as electropotential. What actually happens is that at the start, right, at the instant whereby you place it into a solution, and let's say you somehow measure the potential difference between the two, it will be zero because there's no charges built up yet. But as time proceeds, M will become Mg2+, right? And this will leave a hole here, which represents 2-. So eventually there will be a lot of these holes generated, and when it's at equilibrium, there will be a fixed number of hole here, and there will be a fixed number of charge here. So the potential difference between the two is also fixed at some value, right? So this potential difference, we call it an electropotential, and it is actually related to our equilibrium constant, because equilibrium constant also tells you how much amounts of this and this are present in equilibrium. They are the same concept, right? So this equation can be represented as such. It's just for information, right? So it's equal to RT over NF over ln K. R is your 8.314, T is temperature, N is the number of electrons, and F is your Faraday's constant, right? This is just for info, right? Later on, we will see why this is a useful representation, right? So as long as you have a equilibrium constant, you can calculate the E, basically. This is what it's trying to say, right? So now we see how these two are related. First, if K equals to 1, right? If it's equal to 1, that means the equilibrium doesn't really lie on either side. It's at the center. Ln 1 equals 0, so your E naught will be 0, right? Which means your half cell is at equilibrium, and when K is greater than 1, basically the two signs are the same, right? So the forward reaction will be more likely, and if it's less than 1, the reverse reaction is more likely, just like what your equilibrium constant predict, right? So if you were to refer to your electropotential values, right, it will actually tell you which one prefers the right hand side, which one prefers the left hand side, based on the magnitude, right? Just as what this equation describes. So since electropotential is related to equilibrium constants, whatever that affects equilibrium constant will of course affect your electropotential. For example, your temperature, right? We know that temperature affects your K. But take note, adding more Mg or adding more Mg2+ doesn't affect your K, right? Because we know that equilibrium constant is not affected by adding more reactants, right? But the position of equilibrium is affected. It's not K that is affected, okay? And then by default, electropotentials are always written as reduction potentials, where the left to right reaction is a reduction. So for all of this, from here to here is always a reduction, right? It's assigned this way by default. And just take note, it's always the first species being reduced to the first species on the right hand side, right? For example, for equations as such, whereby you have a lot of species, the redox reaction is actually your HOCl and your Cl2, not the H2O. Same thing for the rest, so don't get confused. Sometimes students think, how come the NO2 become this one or whatsoever, right? It's the first species reduced to become the first species here, right? The rest is just used to balance, basically. So now the separation of charge and hence the potential difference is known as the absolute potential or electropotential. There's no way to measure, right? So that's why I didn't say that it's a voltmeter, right? I just say that there's a separation of charge. There's no way for you to measure this potential without any reference. Now just imagine that you are the only person in this world. You cannot say that you are tall or you are short, right? Because you are not making any reference to anybody. This is something like this scenario, right? You need a reference in order to measure, right? So just now we already talked about one type of half cell, which is your magnesium and your Mg2 plus half cell, and this belongs to your metal ion half cell, right? There can be other systems. I know that you have only learned 3, but the 4th one is equally important as well. If not, I wouldn't have placed it here because it was tested before, right? So you have the metal ion system, you have the gas ion system, you have the ion system, and you have the last one, insoluble solid ion system, right? Remember that question about MnO2 just now, right? MnO2 is a solid, yes, but there's no such thing as an MnO2 electrode because MnO2 is an insulator. How can you make an electrode with an insulator? Right? It's the same as a piece of wood, correct? There's no way of making an conductor. So in order for you to build a half cell of this MnO2, Mn2 plus system, right, you have to coat it around the PT. Another way is, instead of coating it, you can just put your PT inside, throw your MnO2 inside, and then throw your Mn2 plus inside. It's the same, right? Just that these two must be in contact, and the whole thing must be in contact with this thing, right? Either ways is fine. And just for info, your MnO2, Mn2 plus is here. Basically, they can ask anything here and then ask you to draw the half cell, right? You have to know how, including mercury, right? So how do you draw a mercury half cell? Remember, mercury is, now you cannot let mercury sink in. Mercury is a conductor, is not insulator, right? So the trick is just, you know that you add mercury and mercury will sink to the bottom because metal is heavier, correct? So this is your mercury, and this is your Hg2 plus solution, if you can make it into a solution, because Hg2 plus is supposedly insoluble as well, right? Let's say we have one soluble salt, right? This is your Mg, this is your Hg, this is your Hg2 plus. So in order to do it, you just have to do it this way. Attach a platinum rod that's touching the Hg, right? So these two is still in equilibrium and is still in contact with the PT, right? So you have to be flexible, right? This is just one example. And later on we'll see the standard conditions, right? So for now, you can ignore the 1 molar whatsoever, right? We'll see later. And take note that for this case, right, Mn2 plus, you can use any soluble salt of your Mn2 plus. You can use MnCl2, MnBr2, doesn't matter. Because what is establishing the redox system is actually just Mn2 plus. It's not about the Cl minus. You can use MnSO2 as well, up to you, right? Doesn't really matter. It doesn't hinder the reaction, right? So aforementioned half cell electrode potentials cannot be measured directly, therefore you need a reference, right? So the first reference electrode is known as the standard hydrogen electrode, and is of course the most common electrode of the old days. Consists of platinum coated with finely divided platinum, right? Why do you need finely divided platinum? Some people say it's harder for your H2 to slide down, right? Because if it's smooth, you'll just slide down. But I personally think that it shouldn't be because of that, right? This is too naive a solution. The reason is just because you want to increase the surface area. Therefore, you add finely divided platinum, right? Maybe this is a reason, I don't know, but it doesn't sound convincing to me. Electrolyte, you will need 1 mole per dm cube of H+, which basically means pH 0, right? Reagent, H2 gas at 1 atm, temperature 298 kelvins, and we arbitrarily define it as 0 volts, right? This is something like a ruler. Last time they just defined 1 cm as like that. Of course you can define 1 cm as like that and make everything with reference to that, correct? It's also correct, just that they arbitrarily define it as such. This is the, like what I said, old days we use standard hydrogen electrode, but we know that the SHE is very difficult to use because you have to deal with your flammable H2 gas, it's very difficult to maintain it at 1 atm, and the corrosive acid, which is pH 0, it's not very practical. So therefore we prefer to use other kinds of reference electrodes, right? Imagine if you want to use the SHE, you still have to carry a canister of H2, which is very dangerous and it's very bulky. You still have to set up. So nowadays they have other reference electrodes. For example, like the silver chloride electrode, which can be as short as 5 cm and 2 mm in diameter, right? That's like thinner than your pencil and shorter than your pencil, right? So one kind of, and basically you can make everything or anything the reference electrode. It doesn't really matter. It's only a reference, right? So the first reference electrode is called the standard calomel electrode. Later on we'll see why. You don't have to be concerned with the diagram, right? It's an over-complicated diagram of the actual electrode, right? You just have to know the redox equation, right? It's just for info anyways. And the next kind is known as the silver chloride electrode. Both are easier to use and they deal with less harmful stuff, right? However, they have different electrode potentials. For example, as standard calomel electrode, electrode potential is plus 0.268, while for the silver chloride is plus 0.197. But it doesn't matter since it's reference only, right? So how do you convert between reference scales? We know that if you plot this again potential line, your standard hydrogen electrode is at 0 volts, and we know that the silver chloride is 0.197 and the standard calomel electrode is 0.244, right? So basically, if let's say you have your iron system, it is 0.750, right? It's not here, is it? Oh, it's here, 0.77, right? We know that it's 0.77 with respect to your standard hydrogen electrode. So with respect to your standard AgCl, you'll be just the difference, correct? And for this one, it'll be a difference, etc. And why do I put this in? It's because it's tested, of course. It was tested before, right? This is a prelim question. So it says that the AgCl reference electrode is based on the following reaction. They will of course give you, right? So the reduction potential of the Fe2 plus Fe was found to be negative 0.64 when measured using the AgCl Ag reference electrode. So what is the reduction potential of it with respect to standard hydrogen electrode? Right? So you can just draw a number line if you're confused and calculate it, right? You have the answer already? You draw the number line, right? So you know standard hydrogen electrode is here, right? And we know that the Fe2 plus Fe couple is here, your data booklet, negative 0.44, right? So we know that negative 0.44 is on the left hand side, right? And we know that it is negative 0.64 when measured using the AgCl Ag reference electrode. So that means the AgCl Ag electrode must be here, somewhere here, right? And the difference is negative 0.64. So what is this value? It's just plus 0.20, right? So if you have this number line in mind, you'll make your life much easier compared to when you don't know the above concept, right? Can, huh? So this is just one of the many examples that was given before, right? The rest of the examples more or less the same. So next, standard conditions. Just like chemical energetics, electropotential values should have standard conditions to make reference to, right? Standard conditions are temperature 298, pressure 1 atm, concentration is 1 mole per dm cube, right? But why do we need this standard? Where do these standard values come from? If you can recall that equation just now, right? E equals to RT over NF log K. Temperature is quite standard, right? Same for energetics, 298 kelvins. But why do we need concentration to be 1 mole per dm cube for all species? Now let's just pick any equation from here. Let's say this one, nickel 2 plus 2 electron become nickel, right? If I want you to write the equilibrium, the K equation, right? You know that K is equal to 1 over concentration of nickel, correct? Which means if the concentration of nickel is 1, that means K will be equal to 1, right? If K equals to 1, it means it will be at equilibrium, right? Of course, we cannot choose 2, because if it's 2, K will be half. Same concept as the rest, right? If let's say we have, for example, this case, let's say we have 2A plus E2E minus become A2, right? Something like that. And I want you to write the equilibrium constant, same thing, K will be equal to 1 over A plus to the power of 2, right? We must keep the concentration at 1, because when it's 1 over 1 it will still be 1. So it's at equilibrium once again, right? Same thing for pressure, right? So if let's say we turn back into our, if you go back to the half cells, that section, you see that everything is in 1 molar, right? So for example, for the standard hydrogen electrode, right? If you can look at, right here, yeah, correct, insoluble solid / ion, right? You can see that the concentration of HCl is 1 molar, right? Now, what if I use H2SO4? Do you think I should still use 1 molar of H2SO4? The answer is no, right? Because if I use 1 molar of H2SO4, H will be present in more than 1 molar. Take note that it's not 2 molar, because the first H plus is a strong acid, the second H plus is a weak acid, right? So it will be more than 1 molar. So if it's more than 1 molar, we realize that if we sub back into this equation, it will no longer be 1. So therefore we have to use, if let's say we assume this to be both to be a strong acid, we have to use 0.5 mole per dm cube worth of this instead of 1, right? So just take note of that, so we don't make any careless mistakes, right? So next part, non-standard conditions, or your Nernst equation. I believe your notes should have briefly touched about this, right? So this is for standard conditions. Of course, not all, you can't really establish standard conditions sometimes, right? Especially temperature. So what should you do? You can just use a non-standard condition equation, right? So if you can, if you compare this equation with just now the equation, you can see that it's very similar, just that you added some additional terms, right? And all the terms are already defined here. So just think of E with the not, right, means it's at standard conditions. E without the not means it's at non-standard conditions, right? So in order to calculate E at non-standard conditions, you just have to take the E at standard conditions, which you already know from all of these, minus RT over NF ln Q, right? They know that Q in this case is the reaction quotient, right? What is reaction quotient? Reaction quotient, if you can recall, is the same as equilibrium constant, just that we call it reaction quotient because it's not at equilibrium. Why is it not at equilibrium? Because it's non-standard conditions, right? You don't have to know how to use this equation unless the question gives you this equation and all the terms, right, which they did before. Take note N, people always say that N is the number of mole of electron, which is misleading. It should be the number of electrons transferred in the equation. Or you can say number of mole of electrons per mole of equation, right? So it's not the number of mole of electrons, so don't make mistakes as such, right? So one example on how do you apply this Nernst equation. If let's say I give you this equation and then I give you this question, you should know how to do, right? Because I already give you everything. So now, what is the electropotential for the following system when the following concentrations are used? pH equals to 1 at 350 Kelvin. You can see very obviously that it is non-standard, right? So how do you use the equation? I'll just demo, right? So in order to calculate E, you just take the standard potential, which is 1.52, which is already given, and it's also inside here, minus RT over NF. R is your 8.314, T is 350 kelvins, number of electrons per equation, it is 5, right? Followed by a Faraday's constant, which is your 96485, it's really given above as well. And then ln Q. Q is just your equilibrium constant. So if you can recall, right, how do you write the equilibrium constant? You don't include water, right? You include Mn2 plus concentration over your MnO4 minus concentration, right, over your H plus to the power of 8, because the coefficient is 8. So now it's just your job to substitute everything in, right? So remember to convert your pH to concentration of H plus. Okay, and then you should have the answer. You can go back and solve, right? Quite straightforward. You can see that it's about 1.3 something or 1.4 something. So next, measurement of standard electrode potential. We have learned half cell, we have learned reference electrode, so now we'll combine them to make them into a cell, right? So in order to measure the standard electrode potential, right, it's just the potential difference between a SHE and a half cell in which the reacting species in the solution are at molar concentrations of 1 molar, 298 Kelvin, and gaseous species at pressure of 1 atm. This is the formal definition. So to measure the standard electrode potential, you will connect the respective half cells to the reference electrodes using a salt bridge or a salt bridge equivalent, such as a membrane, right? Now, let me ask you a question. Can you just use a wire to connect the two? You have half cell A, half cell B. Can you just connect it with a wire?
Because I use copper, so
Like an inert conductive wire. Can you do it? Do you think it's doable? Why do I do
because
it?
like the salt bridge works by like ionic equilibrium.
What about wire?
So like if it's inert, then
Inert metal, but it's still conductive. Let's say platinum. Platinum is conductive. You can just connect a platinum wire here. Will it work? The answer is it will not work. Take note that the salt bridge function is used to establish neutrality by transferring ions. There's no such thing as transferring electrons to make it neutral, right? Your solution can contain ions, but your solution cannot contain aqueous electrons, right? So if you use a wire, you will fail. So you have to use a salt bridge or a membrane, right? So next, electrons always flow from the oxidation half cell to the reduction half cell, right? This is quite straightforward. So what information can you obtain from standard electrode potentials, right? What can you obtain from all of this? First is your oxidizing or reducing power, right? Like what I said, from the left hand side to the right hand side, it is reduction, right? So the more positive E cell, that means the right hand side is more favored. That means the stronger is reducing power, and vice versa, right? Secondly is your reactivity. If let's say you compare the metals, right? You can recall your reactivity series that you have learned in O levels. Can you recall? Your what? Please send cat monkeys, don't know what, right? So you have potassium, sodium, whatsoever, right? If you can find their electrode potential, you will see that it will fit nicely with your reactivity series. So you can actually use this to predict your reactivity. How? Right? You just have to look at, see the first one is potassium already, right? You just have to look at the E cell value. Most negative means it's the most reactive metal, right? That means it's more likely to form the cationic state and so on, right? So you can actually use this to predict. Therefore, it actually tells you a lot of things. Last one is predict reactions, right? So for one of them, which is the most positive, you will have greater tendency for reduction. The other one will have greater tendency for oxidation because the most negative. So if you place these two solutions together, you will see that the first one will go towards the right hand side, the second one will go to the left hand side, and so on. You'll see more about predicting reactions systematically later on. Right? Protect cell. When a reactive metal in solution is connected to a less reactive metal in its ion solution, electrons flow from the more reactive to the less reactive electrode, and then you can generate a current. So take note of the electron flow and the current flow, right? They are always opposite of each other, right? So in this case, electrons will be flowing from the zinc to the copper electrode. Zinc will be undergoing oxidation. Copper will be Cu2 plus will be undergoing reduction, right? And then you can write the overall equation. So for Sawbridge, you can see that as Zn2 plus continue to be produced, the zinc half cell becomes progressively more positive, right? So if let's say you have the zinc half cell, you can see that if zinc gets oxidized to zinc 2 plus, there will be more and more zinc 2 plus inside, right? So same thing for the copper, right? For your copper, you have copper 2 plus in your solution. So as electrons flow to this, copper 2 plus will become copper. So it will be lesser and lesser copper 2 plus here. In other words, there will be net positive charge building up in this half cell, net negative charge building up in this half cell. So although without a Sawbridge it will still work, but you won't work for long, because eventually charge build up will stop the two, right? So therefore you will need a Sawbridge. Sawbridge contains salts such as KNO3 or something that won't interrupt the reaction. What will happen is the K plus ions will migrate towards this. The NO3 minus will migrate towards this, right? So when NO3 migrates towards this, you will neutralize the positive charge, and for this one, the K plus will neutralize the negative charge. So electrons can still flow in the external circuit. So that's the use of a Sawbridge, right? So there are a few electrolytes that you can use for Sawbridge. Basically, salts which doesn't interrupt the reaction, right? So next, cell diagram is just a shorthand system. Sometimes it can be confusing, right? So oxidation is written first and reduction is written second. So if you were to look at that example, it will be more clear. So if you have a zinc electrode being oxidized to zinc 2 plus, you just have to put a phase boundary, right? Correct, that's phase boundary. And afterwards, it's separated by a Sawbridge double slash, and the other side will be Cu2 plus being reduced to your Cu, right? Of course, most schools will give this example because it's so easy, right? The next example is your phase, your comma, right? When you use comma. So if let's say you have the standard hydrogen electrode, you write it as such. PT is the electrode. You will separate H2 because they are in different phase, and then your H2 gas and your H plus aqueous is again in different phase, so separate them with a phase boundary followed by a Sawbridge, and then the two systems Fe3 plus, Fe2 plus, right? Because Fe3 plus is being reduced to Fe2 plus, but they are in the same phase, so you separate with a comma followed by PT. And then if you look at the example, for the example they say that you have iodine half cell, and then you have the following half cell, and then they want you to write the cell notation. So once again, same thing. First step is you think of which one is being oxidized and which one is being reduced. So since the oxidized one occurs first, right, you write the oxidized half equation. So you're using PT, but you have to keep this in mind. You have to have the half cell in your mind already, right? Whether you are using the ion, the metal ion, or whatsoever, because that will be important for your phase boundaries. So for this case, it's a gas ion system, right? It's similar to your SHE, So yeah, it's the same. But on the right hand side, you have a aqueous system, or you can have a gas aqueous system, right? Because if you dissolve iodine in potassium iodide, you can have I3 minus, which is an aqueous system. If you have aqueous system in aqueous system, you should put a comma. If not, you should put a slash, right? Take note, the I2 gas slash aqueous slash I3 minus means you can put either or, doesn't mean both exist, right? So just take note, right? So as a form of practice, you can just go back and write the self-diagram for all of this, right? It's a good practice. So next kind is your standard cell potential, which is your E cell. The definition is the maximum potential difference between two half cells under standard conditions. Now, why do I underline the word maximum? Right? If you have two half cells, and then you measure the setup already, and then you measure the voltage, you will be the maximum at the start, and slowly it will decrease. Now imagine this is just like a battery, correct? Your battery, of course, after you use some time, people say no more battery. What do you mean by no more battery? No more battery means the voltage decrease, right? How come when voltage decrease, your battery cannot be used? If you can draw the voltage against time diagram, this is how you'll look like. I don't know how, right? But you'll be decreasing, right? For most of your electrical appliances, there's a threshold which they will accept, right? So initially at the start, yeah, got bad. But use until here, the voltage drop beyond here. It doesn't work on your whatever toy car or whatsoever, right? But surprisingly, you can still take out the battery from a toy car and maybe put it in your clock or in your calculator. It still works. Why? It's because smaller appliances, of course, they use less voltage, right? Their threshold is smaller. So even though your toy car cannot use, along this stretch, you can still use it for your clock and whatsoever, and so on, right? So therefore, you shouldn't throw away battery once it stops working. You can still use it for smaller appliances, right? This is the application of your electrochem, right? Anyways, E cell can be calculated by E reduction minus E oxidation, right? And later on we'll see how this equation, which is now, we will see how this equation is derived, right? So whenever you see an equation, always ask yourself, how is it derived? Don't just take it as it is, right? So how do you derive this equation? It's actually very, very simple, right? So if you can recall the zinc system, you have zinc 2 plus 2E becomes zinc, right? The other one is copper 2 plus 2E become copper, right? And we have these two E cell values. So for the first equation, we can just call it K zinc. For the second equation, we call it K copper, right? The equilibrium constants. And we know that the overall reaction is zinc plus Cu2 plus become zinc 2 plus copper, right? This is the overall equation. Now if I want to find the K for this equation, how do I find? If let's say this is equilibrium, let's say, how do I find the K? You have to invert the first equation, correct? If you invert the first equation, K will become 1 over K over Zn. The second equation we don't invert. So in order to calculate K, we just have to take this, multiply by this, right? I think I went through this in chemical equilibrium, right? In order to calculate the net K, you just multiply these two. So if you multiply these two, you have KCu over KZn. This is the equilibrium constant, right? So now remember that first equation, E equals to RT over NF ln K. If we substitute this in to find out the E cell of this equation, right, the equation will become E naught cell equals RT over NF ln KCu over K zinc, correct? So now if I want to simplify this equation, this is just equal to RT over NF ln KCu minus RT over NF ln KZN. Correct. So ln KCU, this is the what electrode? Is this the reduction or the oxidation? Copper is undergoing reduction, correct? So this is the same, in fact the same as the E naught of your copper, isn't it? This is the same as E naught of your zinc, isn't it? Right. So E copper minus E zinc, we know that this is undergoing reduction. We also know that this is undergoing oxidation. So isn't it just this equation? Right? Simple, right? That's why I went through this equation first, right? Because you will need it here. So now, how do we calculate the E cell of this equation? I believe your teachers have told you, just copy down the E cell. Don't swap the sign whatsoever, correct? And then a lot of students get confused. So do I swap or don't swap? Later on we'll see again, right? So for this case, E reduction, which is your copper, right? It's 0.34 minus your E oxidation, which is your zinc. The zinc is negative 0.76, so we keep the sign, and then we will have our value, which is 1 point something. My math not good. This is what? 1.1, right? Plus 1.10, right? So you can just apply this equation directly to obtain 1.10, right? So now the question is, just now we swapped the zinc, correct? So why we never swap the sign? The answer is we actually swapped the sign already. That's why we put a negative here, correct? So we don't have to swap it again, because we'll be performing double swapping. You can either do this, or you somehow derive an equation whereby it's plus. If it's plus, then you can have to swap the sign. Some schools learn the plus method, some schools learn the negative method, right? But I'll just go with the negative method, so you don't have to swap, because you already swapped the sign by putting a negative here. Can you see? Just now we already swapped the sign already, right? Therefore it's divided. Otherwise, I would just have worked from KZN and KCU directly. I wouldn't have put 1 over KZN. Okay, so you have to know that we already swap it. That's why we don't change the sign. Not because your teacher say don't change the sign means don't change the sign, right? Now another evidence of why we should swap the sign, right? If let's say it's not negative, if you were to look at 7, right? Example 7, reverse or not. If you were to look at this equilibrium, you can see that this is exactly the same as the chlorine 2, just that it is the opposite, right? If let's say I ask you what is the electrode potential of this system, your answer should be it is negative 1.36 volts, right? Because you have to swap the sign. Why do you have to swap? Remember just now we defined something called K, right? This K represents Cl2 plus 2E 2Cl minus, which is this, right? Now it's logical to think that if you swap like that, K will become 1 over K, right? If you don't swap, then it doesn't make sense with the equation, right? So that's why we will swap it. Okay, just that, let me repeat, just that for this case, we already swap it by the negative sign, so we don't have to. But for this case, I'm not talking about that equation, so we have to swap it. Okay, so just take note of that. Okay, so the next part, application of your LCP principle to electrochem, right? So aforementioned, electrochem is related to equilibrium K, therefore E naught will affect it if POE shifts, right? So for this zinc system, I use it as example. If you add water to the copper 2 plus copper half cell, your oxidation potential your EO will decrease basically, right? Why will it decrease? Because this is 0.34. If you add water, this becomes diluted, right? This one unaffected because it's solid. Position of equilibrium shift to this side, this will become less positive. If you add NaOH to Cu2 plus Cu cell, what will happen is remember, if you remember your QA, right? If you have copper 2 plus and you add NaOH, you will form pale blue precipitate insoluble in excess. It's the same as decreasing CO2 plus. Is it? Yeah. Okay, so it's the same effect. Using a smaller piece of copper, no effect, right? Because your concentration of your solid remains constant. And then for the adding water to Fe3 plus, Fe2 plus part, no effect because both exist in both coefficient is the same, right? So both will be diluted by the same amount. So no change. Adding some FeCl to the Fe3 plus, Fe2 plus half cell is the same as adding this. So equilibrium shift left, ER will decrease, right? And using FeOH2 solid instead of FeCl2 solid makes no difference, right? So both are the same, right? Let me see. I think for the last one, there's a problem, right? If you use FeOH2, if you use FeOH2, it should be insoluble in excess, correct? So the last one should change. So please cancel the no effect, right? FeCl is soluble but not FeOH, right? So you can then deduce on the change on E cell based on the equation just now, right? So example 8. What will happen to the E naught of the following half cell if more Cr3 plus is dissolved? Will it be more positive, more negative, or what? If you add more Cr3 plus, position of equilibrium will shift left, correct? If you shift left, you will be less positive, correct? Huh? So what if you increase pH? If you increase pH, that means the amount of H plus will decrease, right? If decrease, that means once again position of equilibrium shifts left, it will decrease or become you become less positive, right? What if you add water? Can I say that if I add water, right hand side got 7 water, so water increase, position of equilibrium shift right, and then E naught increase? Can I say that? Is it correct or is it wrong? Correct or wrong? Wrong, huh? Imagine, how can you make water more concentrated? You can't. Correct? So adding water to water doesn't affect the concentration of water because concentration of water is fixed. So if you add water, what you will do is you will dilute the rest. Right? So if you see on the left hand side, you have 15 aqueous species. On the right hand side, you have 2 aqueous species. Right? So you think equilibrium will shift where? Shift left or shift right? You shift left, correct? Because the concentration decrease on the left hand side is more severe than the right hand side. So therefore, position of equilibrium will again shift left. So it will be less positive. Okay? So I will quickly go through 11, the first part. This is how you predict the spontaneity of redox reactions, and it's very, very crucial. And you can use this method to do it systematically. So first is note down all the half equations in your data booklet where x appears on either side, and you repeat for y. You can do it in a table form. Form reduction and oxidation pair for all the possibilities. Take note that if a reagent appears on left hand side, it's reduced, vice versa. Calculate the E cell for all possible combinations and choose one which have the most positive E cell, right? So you have to write the species, the E reduction and the E oxidation, right? For the first example. Right, for species wise, take note that you have FeBr3 and your FeI3, right? For the first species, the one that is being reduced, right, it can be your Fe3 plus, and then the species that is being oxidized, your Br minus, or it can be the other way around, which is your Br minus and your Fe3 plus, right? You can try out all the possibilities, right? For your Fe3 plus being reduced to your Fe2 plus, right? Fe3 plus, maybe the E reduction is 0.77, just copy from your data booklet. While for oxidation, right, Br minus is 1.07, or the other way around, which is 1.07 and 0.77. So now you go ahead to calculate the E cell, right? E cell is just this value minus this value. For this one, you end up with a negative. For this one, you end up with a positive value, right? But do you think it's possible to reduce Br minus? It's not possible, correct? Because Br minus is at the most reduced form. So that means this is the most stable form already, and no reaction can occur, right? Now if you were to do the same for the iodine species, right, you replace this with I minus and replace this with I minus, right? You can see that for the iodine species, right, iodine is here, it is actually 0.54. You get what I'm doing, right? It's either this species getting reduced or this species. This is for the simplest case really, whereby you have two. When you have many species, same thing, list down everything and calculate all the possibilities, right? But for this case, you realize that for the first scenario, it's actually positive, right? Which means that Fe3 plus should react with your I minus, right? So therefore, your Fe3 is not stable, because your Fe3 plus will just react with your with your I minus, right? So therefore, for your FeBr species, you exist as FeBr3, and then for the other one, I think you only exist as FeI2, not FeI3, right? Okay, so we'll stop here. You can go back and try the other example, right? It's the same method.